you works here a little bit.
Yeah.
Okay, I did hit record, so your job is done. We had a few more problems to work out that we started last time on
the same worksheet.
same worksheet. The hang of finding the volumes by slicing and then by revolving. So the idea is, this is still section 6.2. So if we slice region R with rectangles perpendicular to the axis of revolution, whether my region R has rectangles this way, there's my axis of revolution, or that way, there's my axis of revolution. Then we use method of discs or washers. Let's just call it washers. If they're discs, and the little r0, which was pi times the outer radius squared minus the inner radius squared. And then our thickness is either dx or dy. If we position the region with rectangles parallel to the axis of revolution, then it could be a dx situation, and this time we'd be going that way. Or it could be a dy situation, and we'd be going that way. We use the method of shells, and our plan is 2 pi r times h, where in every single one of these cases, the radius is always measured from the axis of revolution. So it might be a function value, it might be just a distance, either in the x or y direction. And then the h is usually given by top graph minus bottom graph, or in this case, right graph minus left graph. So how far did we get on that handout? Do we have it? One or two more?
Yeah, number 8, which is A, B, and C, and then we skip 5.
Okay, we skipped 5. Do we need to finish, come back and get 5?
Only if you want to. I think we're good, but I don't know what everyone else is.
You're good.
Yeah, exactly. What is everyone else?
Okay, so let's go back and get the one that we did, the skip part on number 5. Can you tell me what the region R look like?
And so it's example 3 using shells. So,
Okay,
it's y equals the square root of x and y equals x.
about which axis?
About the x-axis.
Okay, so we did that by the method of washers last time. This time we're going to do it with shells. So y is equal to the square root of x, and y is equal to x squared was that little cigar-shaped region in the first quadrant.
Yes.
Here was y is equal to the square root of x. Y is equal to x squared opened upward. They intersected at the ordered pair 1, 1, and we're revolving about the x-axis. So if we're using shells, right, shell rhymes with parallel. So I know I'm going to take my region and partition it with rectangles parallel to the x-axis. Put it in here just to remind me which variable I'm going to integrate with respect to. How does that tell me which variable I'm going to integrate with respect to? dy. It's a dy, right? I'm chopping up the y-axis. So that means I got to rewrite those equations so that they look like functions of y. So if I rearrange this equation, then this graph is x is equal to the square root of y. Solving that equation for x. Solve this equation for x and you get x is equal to y squared. Right? Those come into play when I do this part. Right? We're doing 2 pi r h, and now that tells me what h is. What is h?
Y squared minus square root of y.
By the way, right graph minus left graph.
Square root of y.
Square root of y minus y squared. So here, h is the square root of y minus y squared, right graph minus left graph. Thickness is dy. So now we need r, and r is measured from the axis we're going around to the middle of that rectangle. What do you think?
And y.
There's going to be some y value that lives in that region. So r is going to be y. So our volume would look like an integral that has our 2 pi r h times our dy right here. I'll put the 2 pi out front. R you said was y. H was right graph minus left graph. dy. And then we go from this y value to this y value. Okay. And we should get the same answer we got in number 3. What was the answer? 3 pi over 10?
Yeah.
Let's do it. Let's do the multiply. I'll have to multiply this out so I can integrate. This is y to the 1/2 times y to the first. And then y squared times y gives me y cubed. Now I can integrate them by adding 1 to the power, dividing by the new power. The 2 pi out front. Let's see, 3/2 plus 2/2 is 5/2. Divide by 5/2 puts a 2/5 right here. Minus y to the 4th over 4. Evaluated from 0 to 1. When we put a 1 in there, 1 to any power is 1. So we just get those coefficients. We're going to have 2/5 minus 1/4. And when we put a 0 in there, we're going to get a 0. And here we get a common denominator of 20. So I have 8 20s minus 5 20s. Inside here, I get 3 over 20. Which is 3 pi over 10.
Same answer we got.
That's always a good start on a Monday, that we got the number that we should get. Don't always guarantee numbers on Monday. Fridays are pretty random too, so Wednesday's the only day you should feel good about numbers. What I wanted to do with that last example is move the axis of revolution away from the x and y axes so that we can implement distances here. So let's go to that last example. So if you remember this right here, this is the secret to life, or at least life in section 6.2. Perpendicular, this is your plan. Parallel, that's your plan. Okay. So, got the secret to life out, but another problem right there.
Very good metaphor.
Too bad. One.
It's an accurate metaphor.
Okay, so the very last problem, what's the region? Somebody read it to me.
The region bounded by the graphs of y equals x squared, y equals 3 minus 2x, and the x-axis is revolved about a given line. Set up the integral necessary to find the resulting volume. And then it has a, b, and c, which tell you
3 minus x, you said?
3 minus 2x.
3 minus 2x. And what else?
And x-axis. And then the a, b, and c is what we revolve around.
Okay, so let's see if we can draw it first. When we revolve it, it's a region bounded by all three of these graphs. Y is equal to x squared, y is equal to 3 minus 2x, and the x-axis. That's what we draw the line first. Line has a y-intercept at 3. And an x-intercept at 1.5. No, at 2/3, right? Y is 0, 2x, 3/2, 1.5, better. Right? That line's gonna go through here. And we've got our parabola. Goes through 1, 1, which not on that line, or is it? When x is 1, y is 1, so it is on that line. Bounded by those two curves and the x-axis. So where are we in this picture?
In that little triangle.
This one down here, right? Bounded by that one, and the x-axis. So it's this little triangle down here. If I were to ask you to find the area of this region, let's just do it, just as a review. I accidentally found this is the ordered pair 1, 1. That's the ordered pair 0, 0. So how would you find the area of this region? In section 6.1.
2 integrals from 0 to 1 and 1 to 3/2.
Okay, so you can do this with 2 integrals, dx integrals from 0 to 1 and then 1 to 3/2.
We can use y integrals and just do one.
We can do a dy integral and just do it with 1. So let's set up the dy integral. The dy integral area is right graph minus left graph, right? And we need those as functions of y. So I gotta take y is equal to 3 minus 2x and write x as a function of y. So let's swap places with the 2x and the y. And then divide by 2. So that's the right graph. I can just put the. What's the left graph going to be?
Square to right.
Good. And what about the numbers that go on the integral sign?
0 to 1.
0 to 1. Okay. All right. We're work any more of that. That was for free, no extra charge for that. Okay, which way are we gonna revolve this, or where are we gonna revolve it?
The first one is about the x-axis, the second one is about the y-axis, and then the final one is x equals -1.
Right here. Well, out of part D, let's revolve about a y value.
Y equals +4.
Is equal to 4. Let's see here, yes. Okay, we'll do all these. But what we've noticed is that it is going to be horizontally simple. So I want to see if we can do all 4 parts of these as a dy integral with horizontal rectangles. Okay, so here we are. There's your typical rectangle. It's going to tell me I'm dy. And in part A, we're going about the x-axis. So disc, washers, or shells? Shells. It's parallel to the axis we're going around. So we need a 2 pi r h dy. This is going to be with shells. So I'm looking at this one as being this x is equal to 3 minus y over 2, and this is x is the square root of y. Here's our 2 pi. To get r, you stand on the axis of revolution and measure your way up to the middle of that rectangle. In this example, we get r from here. We're standing at the line y is equal to 0, and we're going up a certain y units.
So it's just r equals y?
R is y.
Is that always the case?
No.
It's going to change when we move to another.
Okay.
And then h is the what I said with area, right graph minus left graph. So this entity in here would be the h. What about the numbers on the integral side? 0 to 1. And so you can multiply it out, write it with powers, and integrate term by term. So let's blah, blah, blah.
And 2 pi on the outside.
That make sense? Okay, now let's move it around in part B. We're going to go about the y-axis, keeping the rectangle horizontal. So we're still going dy. But what figure is generated if you take that little red rectangle and swing it about the y-axis?
A washer.
You're going to get a washer. So our washer plan was pi outer radius squared minus inner radius squared, and our rectangle is telling me it's dy. So when that makes a washer, the outer radius will be measured from the axis of revolution. So you're standing on the line x is 0, and you're going out this way to the right end point of that red rectangle. And it's going to be some x value that lies on that line. And so do you agree that this is big R? 3 minus y over 2? Going from here to here. And then little r is going to be the square root of y. Okay. Big R is 3 minus y over 2. Little r is the square root of y. And so our volume is our pi. This is always going to be 0 to 1. Big R squared. 3 minus y over 2 all squared. Minus little r squared dy. Okay. Okay. Ready for part C? Here's the line x is equal to -1.
That's a vertical line.
The vertical line, back 1 unit. So let me rub all this stuff off. And keep my red rectangle. Kind of get it back. Still going dy, but now we're going back to x is equal to -1. So is my little red rectangle parallel or perpendicular to the axis of revolution? Perpendicular means we're sticking with the washer plan, right? Big radius squared minus little radius squared. So to get the big radius, we do like we did before. We start from our axis of revolution. When this rotates around, the biggest circle is generated by this tip. So the distance from here to that tip is big R. A minute ago, you said that distance right there from the y-axis to that tip was 3 minus y over 2. And I just made it longer by how much? 1. So take 3 minus y over 2 and add 1 to it, right? Now minus little r. All right, so we're little r, last example was just this, the square root of y, and we again made it longer by 1 unit. So square root of y plus 1. And then close those parentheses, give me the thickness, and then add them up from 0 to 1. Okay. So with the disk or a washer, the big R and the little r are usually one of the 2 graphs. But if you're moving it, then you add to it the distance that you moved it. Unless I moved it over here, which will add another part and I'll put it over here and then you'll show me how to do that one. Okay, so we'll add a part E. I had to do my alphabet song in my head. Am I losing anybody with any of this? Okay, so where is now the line y is equal to 4? Way up there, right? Someone draw a better picture, put writing all over that one. Draw it right here. And I got this little triangular region down here. I'm swinging it that way. And my rectangle is still a dy rectangle. It's just as parallel as can be, right? All right. H is the same. H is right graph minus left graph. So the only thing that's going to change is that radius. Right. In the earlier example, we knew that this distance was y. From here to here is 4, so r is going to be 4 minus y. And our plan was 2 pi RH, RD. Volume is equal to the integral 2 pi R H D Y. 2 pi out. R is 4 minus y. And H is still right graph minus left graph. All these are 0 to 1. So instead of using that picture, let's just make up another example. Draw me the graph of, I guess our favorite parabola has to be in every example. Y is equal to x squared. And intersect it with y is equal to 2x. Let's start flipping that region everywhere. Y is equal to x squared and y is equal to 2x.
Real big picture.
Where do they intersect?
0, 0. Like the easy one.
1, 2, 4.
I have a quick question about the one of the homework problems. So in one of them, gives us a region that's bounded by y equals x, y equals 2x squared, and the x-axis. So I think it's redundant without.
Yeah, I don't think the x-axis should have been there.
Got it.
I think that's just a typo maybe.
Okay, thank you.
Okay, so y is equal to x squared is going to come up through here. Like that. That's going to pair 2, 4. And y is equal to 2x comes as a straight line. All right, so let's generate a solid formed by revolving that region around none of the 2 axes. Okay, so, and we're going to set up a dx integral and a dy integral for each one of them. So in my first one, let's revolve about, let's see, last time we did it, x was where? X was here, it was negative. So let's move the x that way. Let's revolve about x is equal to 3 and find the volume. In part A, using dx as your plan, and in part B, using dy in your plan. So x is equal to 3 is going to be over here, right? And then the last time we did a y is equal to, was it above or below?
Above.
It was above, so we can do a y below. We'll even do an x back here. We'll move that. Let's just milk this one for all it's worth first. So a dx rectangle looks like this. X is equal to 3 is here. So in our very first example, what is our method? Shells. 2 pi r h d x. Figure out what r is and figure out what h is. And figure out the numbers on the integral sign. Think you got it? We're just setting them up. We're not gonna integrate. All right, what did you use for H?
3
Top graph minus the bottom graph. So 2x minus x squared. So now I need R. R is this distance.
That's gonna be 3 minus x.
I like 3 minus x. Does anybody else like 3 minus x?
Yes.
Here to here is 3, here to here is x, so the in between is 3 minus x. Okay, what were the numbers that go on the integral sign? 0 to 2. Any questions, anybody? Okay, using dy, so I'm going to draw a blue rectangle in here for dy. And that blue rectangle around that dotted blue line, what kind of picture are you going to get? Got a washer. So we've got to figure out the big radius squared, the little radius squared, multiply it by pi, and that blue rectangle has a thickness of dy. So to figure out the radii, stand yourself on the axis of revolution and look to the farthest extent. So you're standing here. You want to read all the way back to the outer lip of that big washer, right? So which graph is going to give you that? 2x, right? But remember, we're doing dy, so there's no x's allowed in here. That 2x is what x is y over 2. And this square root of x is oops, x is the square root of y, sorry. Okay, so now this is going to be big R. This is going to be little r. So from here all the way back to here is 3 units. So I don't want to go all the way back to there. I want to stop when I bump into the graph.
Minus y over 2.
3 minus y over 2 is big R. Okay, what about little r?
3 minus square root of y.
Good, good. What are the numbers that go on the integral sign? 0 to 4. They're going to y, so they're going to go 0 to 4. Sound good? They should give you the same answer, so it looks to me like the first one will be easier to do than the second one. Right? Not much easier, but. Okay, what happens if I get a horizontal line somewhere? How about we do the same problem and we revolve about the line?
What happens if the line goes through it? Like, can we? see-
Yeah, we want it outside the region
Okay,
because
yeah,
we'll get,
always.
because we'd have to do some subtracting, so we're not gonna mess with that. So we're gonna get it outside. Where do you want it? Do you want it above the region or below it? Okay, so let's go about the line y is equal to -1 and both. About y is equal to -1, and let's use dx first, and then part B we'll use dy. The -1 is down here. Now you're looking at that red rectangle again, if you want to use a dx. Blue is for dy, red is for dx. You swing that red rectangle around, y is equal to -1, will you get a washer or a shell? Washer. You will get a washer. So our plan for washers was pi outer radius squared minus inner radius squared dx. Can you visualize that, washer? You knew it was washers because there it's perpendicular to the axis of revolution. Okay, so when this makes the washer, the big circle is generated by this farther point going around. So I need to measure the distance from an arbitrary point on that line down to there. So how far is it as a function of x? How far is this?
Yeah.
Sorry, here to here was 2x. I gotta go 1 unit more. 2x plus 1 is big R. What about little r?
X squared plus 1.
That's right, parabola plus 1. Parabola plus 1. And again, the numbers that go with the x's are 0 to 2. Okay, the dy problem here, you're looking now at the blue rectangle, which is my dy rectangle, and we're gonna go that way. Blue rectangle is parallel to y's -1, so that's gonna make the shell. That's the height of the shell. The radius of the shell is gonna be measured from somewhere in the middle of here, all the way down to this line. It's a shell 2 pi RH. dy is our plan. Everything is functions of y. So I'm going to work backwards. What is h?
Square root of y minus y over 2.
Good. Now what is r? What is this
Y
distance?
plus 1.
Y plus 1. Here to here is y plus 1. And our 2 pi, and the numbers now belong to y. Okay? Is that enough? Is that plenty? Make you think of any on your homework that you want me to mention? Yes.
With some of the homework was, I just couldn't find the region they were asking for. So like, oh, calculate the enclosed region, but I couldn't find an enclosed region at all.
Do you have a for instance or?
Yeah, one of the questions sent me was, this is area of the region, it says y equals 13x squared minus 3x cubed plus x. And then the second equation was y equals x squared plus 36x.
So R is enclosed by those two.
Would you like me to get Desmos out?
I know how to graph. I took calculus 1. But I see an x cubed graph with an x squared. So does anybody have an idea of what that's going to look like? That's an x cubed with x terms in it, but now it's going to be upside down. So it's going to go. In other words, it should have both a max and a min to it and then connect some sort of curve. But my guess is that it looks something like that. And that's an x squared, so it's going to look something like that. They've all been shifted all kinds of willy-nilly. So they might run into each other several times. Let's find the points of intersection first, and maybe work our way backwards from there. Set the two graphs equal to one another and see if you can find where they intersect. Which number is this one? Okay, it's on there. Some version of it is on there. It's area, so it's one of the first few. You just want area. Section 6.1. Okay, so we're gonna find the points of intersection. We got 13x² minus 3x³ plus x equal to x² plus 36x. So let's get a 0 on one side. Let's get the coefficient of x³ positive, so let's move everything to the right-hand side. So I'm gonna subtract 13x² from x², so I'm gonna have a minus 12x². And then I'm gonna subtract x from 36x, so I'm gonna have a 35x.
So they intersect at 0.
Yeah, I can pull out the common factor of x. Let's see if we can factor that before we struggle with the quadratic formula. I'm gonna need a 3x and an x. Then I'm gonna need factors of 35 with the same sign that multiplies with this 3 and this 1 to add to 12.
7 and 5.
7 and 5. I put the 7 here, that's 21, 5 there's 5, that's not gonna work. 5 there's 15, 7, no, 7 and 5 is not gonna work. Then factor,
Quadratic formula time.
ew,
Already halfway.
ew. This was a 1x. Then factor,
I'm pretty sure it's on there.
yours didn't factor either, you guys?
I remember using the quadratic formula for the one that was similar. I don't think I have the same numbers.
You guys got some bad numbers.
Minus x cubed instead of minus 3x cubed, and it factored the 7 and
I
5.
know. But you sure the 3 is there? You ain't caught me down wrong or anything.
Oh, my bad, there is no 3.
No. I appreciate that. I appreciate that greatly. Now let's see the factors. But 7 and 5 is 12. So minus 5 minus 7. Yay! So they intersected 0, 5, and 7. Okay, so I don't want the y value, so I want to know which graph is on top and which graph is on bottom. So if you can do this with me in the calculator real quick. Here, I'll get the first one.
0, 0.
They go through 0, 0. I need to know, you only have to put the 5 and say in one of them because they intersect there. Tell me what the y value is when x is 5 and what the y value is when x is 7.
When x is 5, it's 205.
And what about x is 7?
301.
Okay. Next, we need a point in between. So in between 0 and 5, let's plot a 1. This goes through 137. This goes through 1137. Oops, 111, sorry. So what that's telling me is in this interval, the parabola is on top. Okay, so let me get those points on here. 0, 0. Here's 5, 205. And here is 7, 301. So when I plotted the 1, I got a bigger y value from the parabola than I did the cubic function. So here I'm going to take parabola minus the cubic function. I'm now going to draw the picture. When I picked a number between 0 and 5, and I plugged it in here and got a 37. Put the 1 in here, and I got 11. So this y value is taller. So that's the top graph. So now I'm going to do it again. I'm going to pick a number between 5 and 7 and plug it in for x.
Would it be 13 instead of 11 because we still have that 3x cube there. Wasn't it just x cubed?
Oh, yeah, well, it's just x cubed. So how much is it?
13.
13. But that's okay, it's still smaller than 37. Okay, so now you're putting a 6 in there for x. So I have 36 minus 6 times 36, or plus 6 times 36. So that's 7 times 36, which is a big old number.
252.
252? Okay, what about up here? When x is 6 on the cubic graph?
58.
58, so this one's on top. So here I'm gonna take the cubic function minus the parabola. So I don't care what it looks like, I just know the y values are equal at the 3 points of intersection, so they gotta be not equal in between them. I know which one's on top, that's the one I'm gonna write on top. So here I'm gonna integrate for this first region, I'm gonna integrate from 0 to 5, parabola first, minus the cubic function. Then I'm going to add to it the other region. I'm going to go from 5 to 7. And then I'm going to reverse the order. So I just had to have a vague idea that it was going to be vertically simple. I didn't really need the details of the picture. Since I know what a third degree graph looks like in a second degree graph. But when in doubt, you can graph it on your computer and take a look at it, a pretty picture, but I won't make you graph it all the way out. Okay? Funky old numbers after you integrate, no doubt. That's kind of like mathematical hazing. Make you work that one all the way out.
This morning I was working on a homework example and I looked through it. I was like, what am I doing wrong? I realized when I integrated, I had a y squared instead of y squared over 2. It took me like
Whoopsie.
10 minutes to find.
On our write-ups, like I have all my homework written out like this and I just like highlighted it.
That's fine.
Can I just take pictures and like, do
Absolutely.
you want them
Absolutely.
emailed to you? Do you want them on Blackboard?
Put them in the email.
Okay.
Yeah, because I can get a PDF and I can write on them if you do anything wrong.
Okay.
So for your write-ups, if you just want to send me a PDF through my email, that's fine. I saved them all. If you want to turn it in on paper, that's fine too. Clear what I mean by the write-ups? Okay. I think we're ready for section 6.3. How you feeling?
Good.
Great.
Section 6.3, let me see what 6.3 is about. I think we're going to get out of rectangular coordinates. Let me look. Let me look what section 6.3 is. I've slept since the last time I opened this book. Turn up. We're going to look at taking our XY plane, and instead of cutting it up in rectangles parallel and perpendicular to the x-axis, we're going to generate curves by taking a ray with its initial point at the origin, and its terminal point has a pen on the end. This ray has a length of r, but r varies. It can get longer and shorter as it revolves through the origin, kind of like if you look at radar on a weather map, how that little thing plots here the cloud formations. Well, our ray is going to get longer and shorter, and as it's moving, it's going to draw out some graphs. And the point that is plotted in the plane is going to be an ordered pair of the form r and theta, where r is the length of the ray at that instant when that point drops, and theta is the angle formed between the positive x-axis and that ray. we're gonna learn how to graph in polar coordinates. And then heck, if you've got some sort of closed region in any coordinates, don't you want to find its area? Oh, here's the polar plane. We still have an x-axis and a y-axis, but they're not called that. This is called the pole. Drop a ray on here of length r. And then we're going to revolve that ray in a circular fashion. And as that ray gets longer and shorter, it sketches out a graph. That'll be our polar curve. So for instance, this point here has as its ordered pair r theta, where r is going to be the length of that ray, and theta is that angle. So for example, if this in the xy plane is the ordered pair 1, 0, x is 1, y is 0, then theta, of course, is going to be 0, right? And if this is x is 1, r is also going to be 1, right? What if I have a point up here? Maybe that's 1.5 units long. What would the angle be to get us to here?
90 minus
We're in
theta.
radians.
pi/2.
Pi/2, everything's in radians. So the ordered pair here would be the length of r, which I said was 1.5. And then the angle from here to here was pi/2. Okay? All right, so I can have a point like the ordered pair 3, pi/4. Let's plot that point in the polar plane. So first, let's find an angle of measure pi/4. Where would that be?
Be halfway between,
Right here, right? There's the angle of pi/4. Now you get out your ruler and you measure 3 units on that. So let's say that's 1 unit, 2 units, 3 units. So here's the point. R theta is equal to 3 pi/4. Yes.
This is confusing me a little bit because in high school, the polar coordinates I had learned is like the horizontal axis is the real numbers and the vertical axis is imaginary numbers.
There's a relationship between polar coordinates and the complex plane.
So, oh, that's called a complex.
That's called the complex plane.
different.
That's different.
Oh,
Where you represented a number like r cosine theta plus I sine theta, something like that was a complex number.
that and modulus.
Yes.
So that's
Yes,
completely
so that's, it's related, but it's not the exact same thing.
okay.
Complex numbers do appear in the polar coordinates plane. Yes,
So the 3 units that you're plotting, that's along r.
That's how long
regardless,
r is.
Not along the x-axis.
not along the, there's not an x-axis or y-axis anymore. We have a length. That was 1 unit here. I marched out 3 of those. Okay, now I also can name that one point in many other ways. There are many rays that are going to be coterminal with that one. For instance, if I take pi/4 and add 2 pi to it, don't I end up at the same ray? So 2 pi would be 8/4, so 9 pi/4. I can say the point also has as its name 3, 9 pi/4. Right? I could have also formed the angle by wrapping around in the opposite direction. I can make a negative angle. So give me a name for this by doing this. What angle measure is that? And now that angle is negative.
That'd be negative pi.
Would be negative pi/4.
-7 pi/4.
It'd be -7 pi/4. It's not quite 2 pi, right? So that's similar to this, or it's the same point. Or I could get there by adding multiples of -2 pi here, right? So I can change this a bunch of ways. I can also do this. I can say that this is the positive axis, extend it back down here, and that corresponds to the negative of this axis. I can get down to here by going from the positive x-axis to here. Give me a positive measure for theta. It takes me from here to that ray. So you're ignoring that one.
5 pi over 4.
5 pi over 4. But now I'm going to take my point here and project it back. So the ordered pair -3, 5 pi over 4 is coterminal, is another name for this point. Can you give me a name for that point in which both r and theta are negative?
-3, -3 pi over 4.
Perfect. It's -3 pi over 4 is this angle. I go just pi over 4 short of being minus pi. Then I'm on the -3 pi over 4 axis, and I want to project backwards to get me down to here. So that corresponds to the same point. And again, we can do this angle in an infinite number of ways. So there's no unique representation for a point. But we can find it with both r and theta positive, r positive, theta negative, r negative, theta positive, and 2 negatives. So let's do same thing. Let's give us a point in quadrant. I don't know, what's your favorite quadrant outside of quadrant 1?
2, 3.
3. 2, 3, quadrant 2, 3?
No, yeah, the 31st one.
Okay, in rectangular coordinates, an example of a point in quadrant 3 is x is -1, y is -2. So what I'm going to kind of get you to do now is think, if I give you a point in rectangular coordinates, how can you represent it in polar coordinates? Here's x is -1, y is -2. Now I want r to come this long. How on earth can you figure out how long r is? By the Pythagorean theorem.
Root of 5.
That leg is 1 unit long. That leg is 2. I guess I didn't want it 2, did I? Maybe I wanted to go the other way. No, that's gonna be,
R to be a whole number,
yeah, I do want r to be a whole number.
-3, -4.
So, so let's go, yeah, let's go -3 and 4. No, I also want it to be an angle that we know and love. So let's think of our ratios. So how about making y equal to the square root of 2? Okay, or is that too easy? So let's make this the ordered pair -1, negative square root of 2. So we'll take that away. So can you figure out what r is?
Yes, 2, 3.
So that's still not a good one. What do I want to use? What do I want?
-1 and -1 then?
Yeah, that's boring. That's a pi over 4. Let me see. Let's have a 1/2 and a
You could do
square
negative
root of
radical
3
2.
over 2. How about that?
Unit circle.
So you want
Let's do a unit circle one, but let's multiply those by 2. Let's go 1 and square root of 3. How about that? Now that's a ratio that we'll know. How about that? So I want you to plot the ordered pair, -1, -square root of 3. I want you to find the corresponding point in polar coordinates in the 4 different ways. Both coordinates positive, one positive, one negative, and then both negative. Whew, but I had to work hard for that -1, square root of 3, didn't I? How long is R? Because you're using the Pythagorean theorem. Our conversion factor for R is the Pythagorean theorem. Because this is some sort of X coordinate, that's some sort of Y coordinate. So our conversion factor for R is that R squared is X squared plus Y squared. So in our example, our task is to convert this rectangular ordered pair to polar coordinates. So we'll start with X squared plus Y squared is equal to R squared. R is always, well, we're going to do 4 different ways. So let's get the positive R out of this first. How much is it? 2. 2? R is 2. Okay. So what I want you to do is figure out this angle. Come on, Red. Tell me how you got that so quick. Unit circle. Does that mean anything when we say unit circle? To anybody?
Yeah.
Yeah.
I
Let's see what you
remember
know
it,
about
but I
trig.
Got it. Posted.
Let me see what you know about trig. How far back can I go? I can go to,
The one thing I remember.
go to here.
That was drum.
Let's see. Our first quadrant reference angles are 0, pi over 6, pi over 4, pi over 3, pi over 2. Sine goes 0, 1/2, square root of 2 over 2, square root of 3 over 2, 1, and this goes backwards.
Yep.
Can't make a straight line. Okay, so the angle I'm talking about here has the X is -1 and the Y is -square root of 3. Oh, I don't want to go give it away here. My reference angle is this one. That's my reference angle. Let's just call that theta prime. In that right triangle, you have the adjacent side, the opposite side, and the hypotenuse. So for instance, if I wanted to figure out theta, I can use a sine, cosine, or a tangent, right? I know that the tangent of angle theta is which 2 sides? Opposite and adjacent. It's the slope of that line, right? So I can use that to find me theta. My y over x is going to be negative . Y is -square root of 3. X is -1. So the tangent of theta is a positive square root of 3. Well, sure, tangent is positive in quadrant 3. Which of these ratios, this is y, this is x, which of those ratios simplifies to the square root of 3? Pi over 3, right? So my reference angle is pi over 3. So I need to start at pi radians and go pi over 3 more. So what is that red theta right there?
4 pi over 3.
Pi plus pi over 3 is 4 pi over 3. So one name for this particular point is R is 2, theta is 4 pi over 3. Agreed? Let's keep R positive. And give me a negative theta that gets me to there. How much? Negative 2 pi thirds. I have to go 2 jumps over, 1/3, 2/3. Okay, now we're going to keep theta positive. Oops, sorry, we're going to keep R positive. And no, we're going to make R negative. I don't know how I'm going to do this. With a positive theta.
Pi over 3.
So I'm going to need to go to here. And then plot that point backwards. So going to here is just pi over 3. Okay, then I want to go all the way around to here and then plot that point backwards.
Pi over 3.
Wasn't that fun?
Yes.
So there's my conversion factors. If you wanted the other ones, what x is r cosine theta, right? Because cosine of this angle is the adjacent over the hypotenuse, so solve for x. And y is r sine theta. And you know what you get if you substitute these two things into there? You get the Pythagorean identity from trig, sine squared plus cosine squared is 1. So everything moves in a circle. Okay, so that's coordinate wise. Now let's graph. Things in the polar plane are roundish, curvy. They're not polygonal. Made of straight line segments. They're roundish, they're curvy. So what we're going to do next is we're going to look at some polar graphs to know and love. Graph for me, r is equal to 2. Every angle, r is 2. It's a circle centered at the origin of radius 2, right? That's a circle centered at the origin of radius 2.
Is everything based on the origin?
Nope, about to move it, about to move it. Right, if I convert this equation to rectangular coordinates, I could square both sides and get r squared is equal to 4. And I know r squared is x squared plus y squared. So that's the same as the circle, x squared plus y squared is 4. I want you to see what this looks like if you convert it to rectangular coordinates. R is equal to 2 cosine theta. This time, instead of squaring both sides, I'm going to multiply both sides by r. Take that equation, multiply both sides by r, and you get r squared is 2r cosine theta.
X equals r squared over 2.
Let's not even do that. Let's go ahead and replace r squared with x squared plus y squared and replace r cosine theta with x. So now in rectangular coordinates, it says x squared plus y squared is equal to 2 times x. Anybody know what the graph of that is?
Is that an ellipse?
Nope. How about I do this? How about I take that 2x over, group it with the x squared. Ask you to complete the square.
pull it over to the right.
All right, move that 2x over. And now I want you to complete the square on the x.
Complete the square, I forgot about that.
Half the middle term squared. Half of 2 is 1, 1 squared is 1. Add a 1 there, add a 1 there. So that should factor as a perfect square. How does it factor? X minus 1 all squared. Now what's the graph?
Circle.
It's a circle. Where's the center?
At 1, 0.
So r is equal to 2 cosine theta. This is 1, 0, is a circle of diameter 2. Center at 1, 0, radius of 1. So if that's the radius of 1, it's a circle of diameter 2, tangent to the origin. The time?
Almost.
Yes, it is.
What do you think happens if I change this to a sign? Then it becomes a 2y. Goes up there. So what you've learned today is that circle looks like something cosine theta, or r is equal to something cosine theta. And this circle is going to be r is equal to something sine theta. That's the end of circles. We're going to make some other graphs. You'll just have to memorize their shapes. So that you know how to graph the polar coordinates mainly by looking at the equation and not by plotting points. Except next time we'll plot points just to freak you out and then convince you that it's easier to memorize the graphs than to plot points. So you might want to get your little unit circle out and carry it with you for a while until you get all your angles going. I've got one, I think there's one on Blackboard.
Singular
thing I remember.